Hello and welcome to Capturing Christianity. My name is Cameron Bertuzzi. I'm exposing you to the intellectual side of Christian belief. That's what I do on my channel. I think it's safe to say that in today's episode, we are possibly making history. I've received so many messages from people saying that they've been waiting years and years to see a discussion, a live debate or discussion or whatever it is between these two guys that I have on with me today, Dr. William Lane Craig and Dr. Graham Oppy. And today's that day. So Dr. Craig and Dr. Oppy are joining me on the show today to discuss an argument from mathematics for God's existence. Dr. Craig thinks it's a good argument, part of a cumulative case for Christianity, and Dr. Oppy doesn't think that. Well, anyways, thank you guys for coming on the show today. It's so great to have you back. Well, both of you guys have been on the show before, and so we were talking about this right before we went live. Dr. Graham Oppy has been on the show. This is his 5th appearance, if you can believe that. That's crazy. He's been on a bunch of times. And Dr. Craig, this may be your 5th appearance, actually. I don't know. I'd have to go back and check.
I haven't counted.
Right. Well, let me give a brief introduction to my guests if you don't know who they are. Dr. Craig is a Christian philosopher. He holds 2 PhDs, one in philosophy from the University of Birmingham in England, and the other in theology from the University of München. Is that how do you pronounce that? Munich. There you go. In Germany, he's written over 40 books, many of which we actually featured in a recent interview, if you want to go check that out. He's authored dozens of peer-reviewed articles. He runs an online ministry called Reasonable Faith. The link to that ministry is in the description of the video. Dr. Graham Oppy, he's our atheist guest. He's been on the show several times, like I mentioned, including 2 discussions with Dr. Ed Fazer. He holds a PhD in philosophy from Princeton University. His dissertation was on semantics for propositional attitude ascriptions in philosophy of language. Most of his recent publications have been in philosophy of religion, though he's also published in metaphysics, epistemology, and philosophy of science. If you guys want to learn more about apologetics and see intelligent conversations between Christians and non-Christians like the show you're going to see today, make sure to subscribe to the channel and turn on the little bell so you can get notifications when we post new videos. All right, with that, let's get into it. The format for tonight is going to be pretty simple. We'll have 1 hour of dialogue, followed by 30 minutes of Q&A. So we'll get a total of 90 minutes, and we won't go any longer than that at all. Well, let's start with a quick explanation of why the two of you have decided to discuss this particular topic rather than what I think most people were expecting or hoping for, perhaps, the Kalam cosmological argument. Let's pass it over to you, Dr. Craig.
Well, I think that we both felt that that topic had been pretty exhaustively discussed and that it would be much more fresh and interesting to tackle a new topic that we haven't discussed previously.
Right. So that's the basic idea there. They've gone back and forth in the literature on the Kalam cosmological argument several times. And so if you want to see a discussion on that between them two, then go check out some of the articles that they've written. Well, let's get into it. So, Dr. Craig, spend however long you'd like to take to lay out the argument. And we talked about this too. I was listening to your discussion with Daniel Kame on Unbelievable, and one of the things that I wished had happened in that discussion was to give some concrete examples of how the applicability of math to the physical universe provides evidence for God. So, like, what are some concrete examples? But give the examples after you lay out the argument.
Sure. We agreed to use as a springboard for our discussion today an article published by Eugene Wigner in 1960 entitled The Unreasonable Effectiveness of Mathematics in the Physical Sciences. Wigner was a Hungarian-born physicist and mathematician who emigrated to the United States prior to the rise of Hitler's Third Reich. And he went on to become one of the greatest physicists of the 20th century, earning the Nobel Prize in Physics in 1964 for his contributions to the mathematics of quantum mechanics. And in this article, Wigner argues that the applicability of mathematics to the physical world is a mystery that cries out for some sort of explanation. Now, what do we mean by applicability of mathematics? Applicability has to do with mathematics reliability or utility in successfully navigating the physical world. Physicists find that the laws of nature can be expressed as mathematical equations which describe physical phenomena to an astonishing degree of accuracy. And so Wigner's main point in this article was, and I quote, mathematical concepts turn up in entirely unexpected connections in physics and often permit an unexpectedly close and accurate description of the phenomena in these connections. So, with respect to mathematics' role in physics, Wigner notes that mathematics plays an important and what he called sovereign role in physics, which enables us to formulate the laws of nature in the language of mathematics in order for them to then be an apt object for the use of applied mathematics. And Wigner argues that the mathematical formulation of the physicist's often crude experience leads in an uncanny number of cases to an amazingly accurate description in a large class of phenomena. And he gives 3 examples in support. The first example is Newton's second law of motion, F equals ma, where F is the force of an object, m is the mass of the object, and a is the acceleration of the object. Second example is the use of so-called matrix mechanics in the formulation of ordinary elementary quantum mechanics. And his third example is quantum electrodynamics, which is a theory which unites quantum mechanics with special relativity in order to describe electromagnetism. And these examples, which grow in complexity as you go through them, and which he says could be multiplied almost indefinitely, illustrate the appropriateness and the almost fantastic accuracy of the mathematical formulation of the laws of nature. At this point, Wigner then muses, it is difficult to avoid the impression that a miracle confronts us here. He thinks that the success of mathematics in physical theories is truly surprising. And he gives one reason for that, and then I would like to add one. His reason is the a priori nature of mathematical theorizing. Wigner stresses the a priori nature of mathematical inquiry, especially the mathematics that's so valuable in physics. I quote, whereas it is unquestionably true that the concepts of elementary mathematics, and particularly elementary geometry, were formulated to describe entities which are directly suggested by the actual world, the same does not seem to be true of the more advanced concepts, in particular the concepts which play such an important role in physics. Most more advanced mathematical concepts, such as complex numbers, algebras, linear operators, Borel sets, and this list could be continued almost indefinitely, were so devised that they are apt subjects on which the mathematician can demonstrate his ingenuity and sense of formal beauty. And Wigner finds a particularly striking example in complex numbers. These are numbers which are multiples of the square root of -1. He says, and I quote, certainly nothing in our experience suggests the introduction of these quantities. Indeed, if a mathematician is asked to justify his interest in complex numbers, he will point with some indignation to the many beautiful theorems in the theory of equations, of power series, and of analytic functions in general, which owe their origin to the introduction of complex numbers. The mathematician is not willing to give up his interest in these most beautiful accomplishments of his genius. End quote. So who would have ever anticipated then the centrality and the usefulness of complex numbers in physical theory? The second reason I think it's surprising and unexpected is because of the causal impotence of mathematical objects. I would add to Wigner's point the fact that mathematical objects, even if they exist, have no causal impact upon the physical world, so that their applicability in the physical world is, I think, surprising. So the following would seem to be, I think, a suitable formulation of Wigner's argument in his paper. It consists of 4 premises. Number 1, mathematical concepts arise from the aesthetic impulse in humans and have no causal connection to the physical world. Premise 2, it would be surprising to find that what arises from the aesthetic impulse in humans and has no causal connection to the physical world should be so significantly effective in physics. From those premises, it follows that it would be surprising to find that mathematical concepts should be so significantly effective in physics. The third premise states that the laws of nature can be formulated as mathematical descriptions, which are often significantly effective in physics. And then 4, therefore, it is surprising that the laws of nature can be formulated as mathematical descriptions that are often significantly effective in physics. So, given this unexpected applicability of mathematics to the physical world, it seems to me that the applicability of mathematics does cry out for some sort of explanation. And that's where Wigner's article ends. He has no explanation for the applicability of mathematics. As a naturalist, he's simply left with a mystery. He says the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. And that is where his article finishes.
All right, would you like to come in here, Graham?
Sure. So that's really interesting, and I like the formulation of the argument. I tried to write it down while you were saying it. And I think that it's helpful because it points to a couple of places where I would question what Wigner says. So the first premise was something like that mathematical concepts, at least certain advanced mathematical concepts, come from aesthetic impulse. And the idea was that the complex numbers, one of the ideas was that the complex numbers is an illustration of this. I think that that's probably not right. So I remember studying some complex analysis when I was doing my maths degree. And one of the interesting things about the complex numbers is what you can do with them. So you can start with real valued equations that you can't solve analytically using real analytic techniques. But by making a transformation into the complex plane, you can do some complex analysis, and then by purely analytic techniques, out pop some real numbered answers. So that the utility of the complex numbers, at least initially, and the reason why mathematicians were interested in them wasn't aesthetic. It was because there were practical problems that they wanted to solve. They wanted to be able to give exact solutions to these real numbered equations. And it turns out that the only way that you can do that is by taking a detour through complex analysis. I think more generally that Wigner underestimates the extent to which mathematics is about problem solving and overestimates the stuff about aesthetic impulse. I think that typically mathematicians are interested in puzzles, especially long-standing puzzles, but puzzles that they want to solve. And then they're looking around for ways to make advances. And when a long-standing puzzle does get solved, the expectation is that lots of new mathematics will follow on its train. You'll remember when Wiles proved Fermat's last theorem some time back, there were some expressions of disquiet amongst some in the mathematical community because they couldn't see that there was lots of new mathematics that was going to be coming out of it. Right? But the general point, I think, is that Wigner is kind of talking up the wrong thing when he's talking about the reliance on aesthetic considerations, because I think that mathematics is much more about problem solving. Anyway, that's the first thought that you might like to say something about.
I think that it's certainly true that these mathematical concepts do find very practical applications. For example, in something as simple as electrical engineering, complex numbers turn out to be critical and very useful. But I don't think it's true that what drives the working mathematician is scientific utility. The philosopher of mathematics, Penelope Matty, has written eloquently on what she calls maximizing principles in mathematics, which she says are of a sort that is quite unlike anything that turns up in the practice of the natural sciences. She says, and I quote, "Crudely, the scientist posits only those entities without which she cannot account for our observations, while the set theorist posits as many entities as she can, short of inconsistency." And Matty identifies quite a few of these, what she calls rules of thumb, that are followed by mathematicians in choosing their axioms and constructing their theories, such as maximize, richness, diversity, one step back from disaster, etc. And in a similar way, Wigner in his article observes, and I quote, "The great mathematician fully, almost ruthlessly exploits the domain of the permissible reasoning and skirts the impermissible." So it does seem to me that mathematics is driven by this a priori quest for mathematical fruitfulness, the sort of fruitfulness that you said disappointed some mathematicians when Wiles proved Fermat's last theorem. They want to see mathematical richness, but scientific applicability isn't what drives the mathematician. And therefore, these disciplines, it seems to me, are very different in the way in which they operate.
So I don't think anything I said contradicted what you just said then. So I wasn't suggesting that what was driving the mathematicians was applicability to the natural sciences or to the sciences generally, but it's mathematical problem solving, which is not an aesthetic consideration. It's I want to work out what the answers are. Right, so okay, I've got these real valued equations, right? I want to be able to solve them. It turns out the only way you can solve them analytically is by making this detour through the complex plane. So one way of explaining how complex numbers get into mathematics in the first place is from a desire to solve puzzles of another kind. How do I solve these equations, these real value equations? How do I give exact solutions to them? And so I'm thinking that's not aesthetic, it's something else. It's a challenge of trying to get the right answers that drives mathematical innovation. And that Wigner's stuff about kind of inutility and beauty and things like that isn't the primary consideration for mathematicians generally. That was my thought. So I just wanted to disagree with you.
I feel quite certain, having digested Wigner's article, that he understands aesthetic in a broad sense that would include mathematical problem solving. He often talks about how the mathematician chooses concepts on which he can exercise his mathematical ingenuity and develop formal beauty. So certainly mathematical problem solving would be included in this. And I think Wigner would call that broadly aesthetic. I myself prefer to refer to it as a priori. It's not an investigation of the empirical world, but it's a purely a priori discipline that then finds unexpected application in many cases in the laws of nature.
Can I jump in here real quick and
Yep.
can I get like an explain it to me like I'm 5 of where we're at so far in this argument, because everything that's happened so far is just right over my head. So how does this apply to the argument from the applicability of math to the universe?
Okay, so let's go back. Maybe
Pretend
I'll
I'm
get
5.
Bill to read out his first premise again. I mean,
Yes.
that would be that kind of most helpful.
Mathematical concepts arise from the aesthetic impulse in humans and have no causal connection to the physical world.
Right. So I'm thinking about the first bit, just the mathematical concepts arise from an aesthetic impulse. The way that I would understand that, that just sounds false. It just sounds way too narrow. So that's what I was worrying about because it was the first premise in the argument. But what Bill's been saying is that maybe we should understand the aesthetic impulse in a fairly general, a more extended sense than you ordinarily would, so that it would pick up what I think is what much of mathematics is motivated by is unsolved problems in mathematics, and you're trying to work out what the answers are. And that doesn't feel to me like it's an aesthetic impulse, right? It's something much more truth-directed, because you want to work out what the right answers are.
Well, okay, now I would be cautious there, Graham, because, for example, there are alternative set theories, and set theorists are very happy to adopt more restricted axiom sets and explore the consequences, or to adopt additional axioms and to see what those consequences would have, or to opt for an entirely different set of axioms. And so there's a variety of different set theories. And the question isn't, are they true? It is rather, as you say, the sort of mathematical problem solving. So I would be cautious about saying that mathematicians are motivated by a desire to figure out what is true.
So I think yes and no. So there's a controversy amongst set theorists about whether there's one true set theory or not. And there are people like Hugh Wooden who say yes, and then there are many people on the other side who say no. But if you look at some of the things that are controversial in set theory, so where you can take an alternative route and develop an alternative set theory, so you can do set theory without choice or without the continuum hypothesis, to pick two examples.
Yes.
Most working mathematicians are perfectly happy to accept both choice and the continuum hypothesis. And sure, you can explore what happens if you gave them up, but if you look at what, so for example, to go back to the example that we were talking about before, Wiles's proof requires, that is his proof of Fermat's last theorem, requires the axiom of choice. Very few people have objected to the proof on the grounds that it assumes choice. Most working mathematicians think that's just fine. And that view is consistent with thinking, okay, what would happen if you gave up choice? What would set theory look like, right? But that's just a different kind of, problem that mathematicians might be interested in, which doesn't undermine the idea that if Wiles's proof is a proof, it shows that what Fermat said was true. Right? That's the. So I'm not sure whether that's entirely satisfactory. Anyway, maybe we should move on to another.
Well, let me get to Cameron's question about how would we explain this to a 5-year-old. Suppose you're trying to figure out how many gallons of paint you need to paint the floor of the playroom. Well, what you would do is you would, say the playroom is square or rectangular, you would measure the distance in feet one way and then the distance in feet the other way, and then you would multiply these together to figure out how many square feet are in the room, and then you would find out how much paint you need, say, per square foot, and that will then tell you how much paint you need to paint your room. That's an example of the applicability of mathematics. You can figure out how much paint you need by mathematics. Now, that is very, very elementary, but that's what you asked for. Wigner's point is that when you get into relativity theory, quantum mechanics, quantum electrodynamics, there you have mathematical equations of breathtaking complexity and astonishing accuracy in describing the physical phenomena. Is that clear?
Yes, that's very clear. But it's not clear where the disagreement was happening, how that relates to the example that you just gave.
And it'll be hard to bring it out in respect of that example, because it's quite plausible that the mathematics that we're using there was originally developed for practical applications. So if you think about elementary arithmetic and elementary geometry, it was precisely because we wanted to do bookkeeping and work out how to apportion odd-shaped plots of land equally amongst heirs and things like that, that elementary mathematics developed. So it was designed precisely for its application to real world problems. And Wigner's worries don't come up in connection with elementary arithmetic, for example.
Right, and he grants that point.
Yeah. So
because
it's not
those are necessary.
going to help. So you want a different example. You want one, Cameron, you want an example where there's something a bit more uncanny about the applicability. So go back to the concepts that Wigner picks out, so the complex numbers. When you think about the square root of -1, right, the kind of defining thing for the complex numbers, and then you think about electrical circuit theory, and you wonder what on earth could the square root of -1 have to do with the equations that we use to describe current flow in electric circuits, or a bunch of other applications to the natural world of the complex numbers. Then it's puzzling, you might think, in a way that the applicability of elementary arithmetic or geometry isn't. Bill, does that sound about right?
Yes, I liked that. I thought that was quite clear.
And then what's the next step?
Well, the other thing was that mathematical objects have no causal connection with the physical world. Even if you think they exist as abstract objects, usually beyond time and space, but which are causally effete. They have no causal powers and therefore have no causal impact upon the physical world. If per impossibile, all of the mathematical objects were to vanish overnight, it would have no impact upon the physical universe in which we live. Now, given that, and that's if they exist. Of course, if they don't exist, if you're an anti-realist about mathematical objects, then obviously they don't have any causal impact upon the physical world. So given that absence of a causal connection between mathematical objects and the physical world, it does seem really surprising that the physical world should be describable in such detail and complexity by these mathematical objects.
Graham, is there anything that you disagree with so far?
So the thing that Bill was just saying isn't in the Wigner paper. This is his own edition. And I'm not sure, there's a big dispute to be had about whether the objectivity of mathematics requires objects. And you might think that you can not tread the path of the fictionalist, but also not be a Platonist, right? And it would require some argument which surely we don't have time to go into to consider whether that's an option or not. So unless it comes up in the later discussion, I would prefer to put aside the dispute between Platonists, fictionalists, and all the other sort of accounts of the ontology of mathematics, because our question is more about the application of mathematical theories to the world, and that may not turn on any questions about whether there are mathematical objects.
Well, now,
So
actually, I agreed with that, Graham, because my point was that whether you are a Platonist and a realist, or you are an anti-realist, in either case, there's no causal connection of mathematical entities with the physical world. They can't influence the way physics operates. And so it's astonishing then that you would have these mathematical descriptions that enable you to describe and to predict how the physical world is going to behave.
So I think we should go on a bit, and we'll come back to this point. Yeah. The other thing that I'm hoping that we're going to have time to get to the argument about God. I'm a bit worried that we won't, at the rate this is going. The other thing in the argument that you attributed to Wigner that I wanted to ask about was the claim that the laws of nature can be formulated in the language of mathematics. That seems to suppose that we know what the laws of nature are. And that seems to me not to be so. It's true that we formulate scientific theories and they have principles in them, but almost always it turns out that we end up thinking that those principles are false. If those principles are false, then they're not laws of nature.
Here, Wigner's brilliance emerges in his paper. I am just amazed when I read the paper how he anticipates these objections and preempts them. He makes a point himself in the paper that he is not claiming that there is a unique description of the physical laws that govern our universe. What he says is that we can formulate these mathematical laws of nature, and there could be different formulations of them. There could be, he's not claiming that they're unique, but we can formulate these laws of nature and then apply them, test them, and they turn out again and again and again to be accurate in describing the physical phenomena, the way the world appears to us. So I think that premise is formulated by Wigner in such a way as to preempt the objection that we don't know the final form of the laws of nature, that they could be variously formulated, or that they may not even describe the physical world in itself, but simply the phenomena, the physical phenomena as we apprehend them in science.
Okay, so let's think about an example. So maybe this will make Cameron happy, right? A concrete example. So think about classical mechanics, right? And think about what happened in the very early 19th century. So there's Adams in England and there's Leverrier in France doing calculations using classical mechanics. And eventually Leverrier says to Galilei, point your telescope at this point in the sky and you'll see a planet that's perturbing the orbit of Uranus. It's the explanation for why, And so Galilei goes and points his telescope there, and lo and behold, there's Neptune. Right, this was how Neptune was discovered. Yes. It was a prediction of classical mechanics. But the problem is that classical mechanics is a false theory, right? Use it to try to predict the precession of the perihelion of Mercury, it gives you the wrong answer, right? So presumably it can't be that this theory's accuracy was due to its getting the laws right? It's a false theory. It's not just that it's accurate.
Well,
the puzzle is that the theory is false and it's still giving accurate results. You can't explain the accuracy of the results in terms of it's hooking on to the true structure of the world or hooking onto the laws or anything like that, because we know it doesn't. So back to you.
What is correct, I think, is to say that the laws of classical mechanics are approximately true, that they are true within a certain range. And this is not so much falsified as made more precise then by special and general relativistic laws. And there's no claim here that we've got the final formulation of physical laws. Rather, with increasing accuracy, to often astonishing degrees, we seem to be able to describe the physical phenomena. In other cases, the descriptions might be more approximate, but this is no more problematic than saying that I have a watch without a second hand that will accurately tell me the hour and the minute of the day, but it won't give me the second, and that to get the second, I need a more accurate watch. And if I have a watch with a second hand, that still isn't going to give me the current nanosecond. I'll need an atomic clock for that. So the laws of nature can approximate accuracy with different degrees of specificity.
Okay, so that sounds sort of right. The relationship between mathematics and the physical world is one of fit to within acceptable limits of tolerance of empirical predictions, in some cases, but not all. And that's general. So whatever theory we're talking about, it's got a range of application, and outside that range of application, it doesn't give you the right results, and so on. Then the question's going to be, or at least one question's going to be, what's uncanny about that? Why not just think that that's what you'd expect given the power and flexibility of mathematics? Because now we're not talking about some amazing fit between the mathematics and the true structure of the world. We're talking about our ability to make models that will give you the right results across some domain to within some specified tolerance, some limits of accuracy. So when Gally points his telescope to the sky, Leverrier's calculations accurate to within 1 second of arc, but when you calculate the precession of the perihelion of Mercury using Newtonian theory, it's just wrong. It's out by so much.
Mm-hmm. Yeah, I guess I just don't see the problem there. I mean, the equations were sufficiently precise to yield a real world result, the discovery of the planet Uranus that is out there. It is a real world result that was possible because these mathematical equations were accurate to a sufficient degree to be able to predict such a phenomenon. And the equations of quantum mechanics and general relativity theory are more accurate to orders of significance in terms of how accurate these theories are. So there is a significant fit that enables us to get along in the universe, to get along in the world because of mathematical applicability.
Okay, maybe now would be a good time to advance to the argument for God that you want to make.
Sure.
So can we move on to that?
Yes. Now, you remember Wigner ended his essay by saying that the applicability of mathematics is a miracle which we neither understand nor deserve. But Wigner never actually considered theism in his essay as to whether or not that might not furnish a good explanation of the applicability of mathematics. And my view is that theists will have a considerably easier time than naturalists in explaining the applicability of mathematics to the physical world. And this will be the case whether one is a realist about mathematical objects or whether one is an anti-realist about mathematical objects. On the one hand, if you're a realist, then the fact that reality would behave in accord with these causally effete abstract objects beyond space and time is, in the words of philosopher of mathematics Mary Lang, a happy coincidence, which just seems incredible. Mark Balaguer, who is another philosopher of mathematics, has said the idea here is that in order to believe that the physical world has the nature that empirical science assigns to it, I have to believe that there are causally inert mathematical objects existing outside of space-time, which is just inherently implausible. Now, by contrast, the theistic realist can argue that God has fashioned the physical world on the structure of the mathematical objects that he has chosen. And this is essentially the view that Plato defended in his dialogue, the Timaeus. On the other hand, suppose you're an anti-realist about mathematical objects. Then again, it becomes inexplicable as to why the physical world would behave in accordance with these pretend entities that don't really exist. But if you're a theist, what you can say is that God has fashioned the physical world on the mental plan that he had in mind, so that the physical world has the structure that God had conceived prior to creation. And this is the view that was defended by the Jewish philosopher Philo of Alexandria. So whether you go with Plato or with Philo, it seems to me that the theist has a much easier time of explaining the applicability of mathematics to the physical world than does the naturalist. And so the applicability of mathematics counts in favor of a theistic view of the world.
Okay, so to check that I understand what's going on here, and maybe I don't, it sounds as though the story is committed to something like this. Mathematical theories apply to the physical world because the structure of the physical world is an instantiation of mathematical structures described by those mathematical theories. So God makes the world with a certain physical structure because there's a certain mathematical structure that God wants to have the physical world instantiate. Right? So that's a kind of Pythagorean idea, right? Number is really fundamental. Fundamentally, the structure of the world is mathematical structure. Is that part of the idea or not? Because I'm trying to think about what does God do here, yeah. Right? Is that the idea?
It's part, but only part, Graham, and that's really important to see. Even if you say that the physical world exhibits this complex mathematical structure that it does, and that's why mathematics is applicable to it, that leaves unexplained on a naturalistic metaphysics why the world should have the fantastic, complex mathematical structure that it does, that is described by general relativity and quantum mechanics. So that's part of it, but that's not the whole story. By choosing examples like complex numbers and infinite dimensional Hilbert space, Wigner implicitly precluded the explanation that the reason mathematics is applicable is simply because the physical world instantiates these structures, because these kinds of structures cannot be physically instantiated. And this is the burden of Mark Steiner's book, The Problem of the Applicability, the applicability of mathematics as a physical problem. Steiner gives example after example of applicable mathematical concepts which cannot be physically instantiated. And so what you've expressed is only a part of the story. And here again is where theism emerges, I think, is a better explanation than naturalism, because God can create a world that will operate in such a way that the use of Hilbert spaces and complex numbers and other uninstantiable mathematical structures can be useful in describing and predicting physical phenomena.
Okay, so I'm not sure I'm following this now. So I'm still trying to work out on your theory what God's doing. So part of it is that God makes the physical world to instantiate a certain kind of mathematical structure. But God also picks the structure so that so that you can use other mathematical theories to investigate that structure, but we don't suppose that those other theories instantiate the structure. There's some other relationship that holds between them.
Yeah.
Yes. Okay. Now, where in that picture, so now maybe it's now becoming clearer what the idea is in relation to, say, the example of Neptune, the discovery of Neptune, right? The theory doesn't latch onto the structure. The theory is false, right? So it definitely doesn't latch onto the physical structure that the world exemplifies.
Well, again, I would say that it does to certain degrees of approximation.
That I'm not sure that I understand that, right? And maybe there's a view.
It gives you an approximately true description of our solar system.
So there's a view that some people have about, say, the relationship between general relativity and Newtonian mechanics, or between quantum mechanics and Newtonian mechanics, that there's a kind of quantity and you let it go to infinity or you let it go to zero and the other theory falls out, then Newtonian mechanics falls out as a special case, and that's how you explain how the one theory is an approximation to the other. It's not clear that that's right, but it's also not clear how we're going to understand this idea that the theory's an approximation, that the one theory's an approximation to the other. So let me try something else. Consider what Michael Friedman says in his book on space and time about the relationship between general relativity and Newtonian theory. It turns out that we can write both these theories in the language that was originally, the mathematical language that was originally invented in order to make it possible to represent general relativity, but you can rewrite Newtonian mechanics in that language as well. And when you compare the two theories, the difference between the theories is that Newtonian mechanics postulates some extra structure. It's not that it postulates less, it postulates more, right? Now, how can it be that that's a... How are we going to think about that as an approximation to the truth, right? When what it's done is it's postulated extra stuff that meant that it went wrong.
I think it would depend on whether or not that extra structure needs to be excised to get a more accurate description of the physical phenomena and to predict future results of experiments. As you may know, I myself think that the general relativity is wanting in structures, space-time structures, that they deleted some important things like hypersurfaces of absolute simultaneity that tend to be restored in, I think, astrophysical cosmology. But be that as it may, whether the structures are additional or deleted. It would be a matter of the degree to which the mathematical laws give us an accurate description of the phenomena and enable us to predict future phenomena. As you say, Leverrier's theory didn't allow us to predict the perihelion of Mercury. We needed relativity theory, general relativity theory, to make that prediction. So I think that theism has more explanatory power than naturalism with respect to this unexpected applicability of mathematics.
Okay, so maybe now I should address that question, because in a way, I feel like I don't have enough physics really to kind of assess Wigner's claims about whether there's this unreasonable effectiveness there or not. And I thought about lots of examples and wondered, there's lots of examples of, for example, simple physical problems in classical mechanics where you set up an equation and you to model some situation and you solve it, and then you notice that there are solutions to the equations that just don't make any sense, and so you ignore them, right, on the grounds that they're not physical. Right, there are all these kind of interesting questions about the ways in which we. So an example, right? Imagine a cliff top, and you're throwing a rock into the ocean, right? So you've got you set up your model, have sea level at 0, the height of the cliff's h. There's some angle that you project the rock. You get an equation of motion, and you work out some time at which the rock intersects with the water. Now your equation is a parabola. And so there's another solution where it intersects the x, x equals 0, the y-axis, at some negative time, some earlier time. And when you look at that, you don't think, so maybe there was an anti-rock and it tunneled up through the cliff and then it was annihilated when the... Yeah. What you do is you say, that's not a physical solution.
Yes.
Right? And that's a kind of universal thing in physical, in kind of modeling, physical modeling of the universe, right? And so, I wondered about the bearing of that on some of the examples that that you've used previously, and some of the examples that Wigner gives in his paper. For example, right, there's Dirac's prediction of the positron, right? But Dirac also predicted magnetic monopoles, which we haven't yet found. What if we never do? What if there aren't any? Right, then presumably the magnetic monopole is just going to go the way that in my simple example, we just say, well, it was an artifact in the model. It didn't correspond to anything in physical reality. Yeah. Once you start thinking about all of the many, many failed predictions from physical theories, right, that correspond to this success where there's the positron, you might wonder whether it's really true that there's any uncanny effectiveness here, or whether it's what's rather the case is just that we forget about all the successes and remember the one or two successful cases. So I'm kind of worried about, again, I don't have any data. I don't know. Who keeps a record of all the failed physical predictions, the physical theories? I don't know if there's anything uncanny there or not.
Well, both Wigner and Steiner discuss this fact. The failures, the mathematical failures outnumber the successes. There's no doubt about that when you think about it. The realm of mathematics is infinite. The physical world is finite. So, of course, most mathematical concepts or formulations will fail to apply. But I don't see the cases in which mathematics fails to apply does anything to explain the cases in which you do have this breathtaking accuracy and detail of mathematical descriptions of the universe. I think you can acknowledge the failure of many mathematical concepts to apply and of laws of nature that are false, but that just doesn't do anything to render it likely that on naturalism you would have this sort of mathematical precision characteristic of the physical phenomena.
So I'd like to jump in just real quick. Well, first of all, got to mention that we're about to move to Q&A, like in just a few minutes.
Okay.
So, but I do have one thought on this, is that, Graham, it sounds like if we could split the argument into two stages, stage one being about whether or not the universe or math does apply or does have this sort of uncanny applicability to the universe. If we labeled that stage one, and then stage two is how do we explain this? Is it evidence for theism? It sounds like you're wanting to go back to stage one and say, well, I don't really know if mathematics does have this uncanny applicability.
Right, so that's all I've argued about so far. But let me say something about the argument, right? Because I think that it's not true that naturalists have no resources here. So suppose it's true that there's this fit between mathematics and physical structure, right, of the kind that we're imagining. There are versions of naturalism that can explain this in a very straightforward way, right? And so one of the versions of naturalism that can do this is one that I've been playing around with for about a decade now. And so let me give you the kind of tenets of the theory that you need in order to explain the effectiveness. Right. You may, when I get to the end of it, you may think it's, disappointing that it turns out that this is the way the explanation goes, but it's definitely an explanation. So start with this, a theory of modality. So every possible world shares some history, initial history with the actual world, diverges from it only because chances play out differently. Right, so that's all the possibilities there are. The only possibilities that you need really are for chance. And we're talking metaphysics here. We're not talking doxastic possibilities or epistemic possibilities. We're talking metaphysical possibilities. So that's all the possibilities that there are. The laws are necessary. The boundary conditions are necessary. This is true. It doesn't matter whether we're thinking about one universe or many universe model. So we're supposing that where contingency comes in is in the outplaying of chances. That's the only place that contingency comes in. We suppose also, and this is the only kind of new assumption that we're going to make to go along with the kind of metaphysical picture that we've already outlined, which is going to be a naturalistic picture, is that the laws and the boundary conditions are amenable to mathematical formulation. On that assumption and given the other assumptions, it just turns out that it's necessary that that's the case. It couldn't possibly have failed not to be so. Now, add in a couple of other things that I don't really need, but that are also part of this picture that I developed when I was thinking about the origins of the universe. It had nothing to do with the applicability of mathematics. There's no explaining why something's necessary. Once you get to the postulation of necessities, you've reached the end of the explaining that you can do. And last of all, if you've got a non-modal claim, P, and you believe that, or you accept that necessarily P, then it's being necessary that P explains why P. Okay, so now, given that, we have an explanation for the effectiveness of mathematics, which is that it had to be. Because it had to be, it's so. Right? And it just falls out of the picture. Now, that's a naturalistic story that has an explanation. You might not like the explanation, but at least for me, it comes for free from things that I've said elsewhere.
Yeah.
Right?
Well, I hope that our listeners have understood your alternative, because honestly, Graham, I think it takes more faith to believe that than it does to believe in God. The claim, for example, that the mathematical formulation of the physical world is necessarily true just doesn't seem to be correct at all. There might have been no physical universe whatsoever, in which case mathematics would not be applicable because there would be no physical universe, or there might have been a sort of chaos. Albert Einstein wrote to Maurice Solovine in 1952, "One should expect a chaotic world which cannot be grasped by the mind in any way. One could, yes, one should expect the world to be subjected to law only to the extent that we order it through our intelligence. By contrast, the order created by Newton's theory of gravitation, for instance, is wholly different. Even if the axioms of the theory are proposed by man, the success of such a project presupposes a high degree of ordering of the objective world and thus could not be expected a priori. That is the miracle which is being constantly reinforced as our knowledge expands." So even so great a mathematical physicist as Einstein thought that it was a contingent matter that the world should exhibit this sort of mathematical order, that we should have expected, on the contrary, a chaotic world.
Well, let's do this. Let's get a response from Dr. Oppy, and then we'll move to some Q&A. So unfortunately, we do have to move on.
So when you talk about expectation, you may be talking about something epistemic or doxastic. Mm-hmm. I was talking about metaphysics. I was doing metaphysics. And my claim is that this is the best metaphysical theory. Right? I'm not saying that it's true a priori. I'm saying that it's the best metaphysical theory when you take everything into account.
Can you specify, Graham, for us in a sentence or two, why is it the best metaphysical theory in your view?
Because if you think about the goal of theorizing, what you're trying to do is strike the best balance between minimizing all of your theoretical commitments and maximizing the explanation that you can do. And I think that this theory strikes that sweet spot. That's the reason. But there's a lot of data, and there are hundreds of data points that you have to think about if we're going to compare this theory, say, with a theistic theory. So I've written elsewhere at considerable length about why I think that you should prefer the naturalistic story to the theistic story. It just turns out that the naturalistic story, see, because this is the point, when you formulated your theory, you said naturalists just have no explanation. That's not true. Here's a naturalistic theory that does have an explanation. And what needs to be argued is about which one is the better theory, and that's not something that's settled by these considerations. It's settled by general considerations.
Okay, it didn't sound very explanatory to me, but we'll leave it at that.
Well, do you think that you can't explain why something's the case by pointing out that it's necessary? Because that's all that's going on here.
Yeah,
right? I mean,
the problem is, it's really a way of avoiding explanation by just begging the question and assuming that it's necessarily the case. And that is implausible and certainly not incumbent, or there's nothing that would lead us to think that that's true, which is why I asked why you thought it was the best. It's not really an explanation.
So that's not right, though. It's not assuming, right? We've got two theories and we're comparing their virtues. The theories are what they are. They say what they say. It turns out that on this naturalistic theory, there is an explanation. The explanation is that this stuff's necessary, right?
I think that's why it holds. Right,
and so now you have to compare the two theories, right? But this is the point. You have to compare them on the total data in order to see which one's the best theory. And when you do that, I say what you find out is that the naturalistic theory is better than the theistic theory, right? And in order to argue that, you can't point to your dissatisfaction with this particular, my theory explains it differently from the way you do, so I'm not satisfied with what you do. You have to look at the big picture.
All right, let's move on to some Q&A here. So there's a lot of different questions on this topic, so it'll open up some new things to talk about. From Indirish, he says, Dr. Oppy, isn't the relative disdain of the four-color theorem and Fermat's last theorem exemplifying exactly what Dr. Craig is claiming? And this happened earlier in the discussion. This super chat came in earlier. That beautiful proofs are more important and the applications are secondary.
I don't think that there's disdain for the four-color proof, right? It was a proof. The problem was that it wasn't the thing that's true is it's not a beautiful proof. It was a computer proof. It was done by kind of an exhaustive consideration of cases. But that doesn't undermine the result, right? There was a serious question that people wanted to solve, and the important thing was we wanted to know the answer. Now we do, right? So I don't think that that there's disdain for the four-color proof. There's regret, perhaps, that we haven't come up with a complete analytic solution for it. Okay,
right,
Bill, you might want to jump in on this.
No, I have no further comment.
All right, we have another super chat from, I'm not even going to try to pronounce that name. He says, Dr. Craig, if mathematical concepts arise from the aesthetics of the mathematician, would there be causation? If so, does the applicability, it looks like English might not be his or her first language, so it's difficult to put this into words. If so, does the applicable causation of at least one abstraction, for example, beauty, not apply to the number 7?
No. Wigner's argument is quite independent of the concern I have about no causal connection between mathematical objects and the physical world. His argument concerns simply the a priori way in which mathematicians pursue their discipline. You wouldn't expect it to be so physically applicable when it's pursued in that way. My point was that whether you're a realist or an anti-realist, mathematical objects don't have any causal impact upon the world. And that would be the case with beauty, too. If you think that beauty is a sort of Platonic form, if it's an abstract object, it doesn't come into contact with or do anything. I think what he means is that mathematicians seek beautiful theorems or proofs, but that's not to say that the abstract object beauty is causing them to do this.
Is there anything you'd like to add, Graham? Okay. Next super chat from Cranman Photo Cinema, and he is our videographer. He sends in super chats all the time. It's from John. He says, "Why?" Yeah, he does. He says, "Why would the surprise of the applicability hinge on aesthetic impulse but not problem solving? Seems that it would still be surprising on the latter." No?
That's for Graham.
Would you like me to repeat it?
I think that's a kind of misunderstanding of what was happening in the earlier part of the discussion, because we had an argument, and the first premise of the argument was a premise about aesthetic impulse. And so the question was that premise true? Because when you evaluate an argument, you kind of, you think, is it valid? Are the premises true? It may be true that you can rewrite the argument in terms of something else, and that would be fine. That doesn't mean that you shouldn't go back and try to get the premises right. So that was the point of at which that is that clear, or do I need to repeat what I said?
I think it's okay.
So Bill gave an argument, and the first premise was, I can't remember the second part of it about causal impact, but the first bit was mathematical concepts arise from an aesthetic impulse. And I thought that's just false, right? So the premise is false. At the very least, we need to reformulate the argument to make it work. Now, it might be true that if mathematical concepts arise from problem solving, you can make the argument go through. That would be fine. It wasn't. We
was
were
just the
trying
first part.
we're trying to understand what the argument should be at that point. That was the point of the discussion.
It did seem to me, Dr. Craig, that part of the argument was not necessary.
Well, this is Wigner's attempt to justify why the applicability of mathematics cries out for explanation. And I took it that would be the point that Graham would dispute most vociferously, that he would say that the applicability of mathematics to the physical world isn't something that cries out for explanation. And if the critic takes that point of view, then these two arguments as to why it is surprising that mathematics should be so applicable in describing the physical phenomena so accurately do become very important, namely the a priori nature of mathematics, and then secondly, the lack of a causal connection.
All right, let's move on to another question from Chris. He says, does the fact that mathematics always describes physical laws instead of randomly describing them mean anything for the design of the universe?
Well, there is the argument from fine-tuning, for example, which tends to be related to this, namely that when you look at the mathematical equations that describe our universe, you find appearing in them certain constants that fall within an exquisitely narrow life-permitting range, and that cries out for explanation as well. So this would be an example of where it's not just the mathematical applicability of the equation, but it's also the values of the constants that are in those equations that reinforce your impression that there's something here that needs to be explained.
Would you like to say anything else on that, Graham? And by the way, would you mind, Graham, taking like half a step? There you go.
Have I moved slightly? Sorry.
Beautiful.
I knew that was going to happen. I want to ask Bill a question. Is that okay? It's related to this point, but slightly tangentially. So the question is this: could God have freely chosen to make a physical world in which it was not the case that mathematical theories apply to the physical world because the structure of the physical world is an instantiation of mathematical structures described by those mathematical theories? Well, so could God have freely chosen to make a world in which that was not the case?
Well,
so let me...
Yeah, okay, sorry.
There are two options, right? If not, then it seems that what you're going to end up saying is that it's necessary that if there's a physical world, mathematical theories apply, which means you just end up agreeing with what the naturalists said, right? That will be the explanation. On the other hand, if it's true, then it looks as though it's just now a brute contingency that mathematical theories apply to the physical world for the reason given, because it's brutally contingent that God chose to make this world rather than other worlds that he could have made instead. We don't have an explanation, right? When you get to free choice and you think, why this rather than that, there's no explanation now to be given of why you ended up with one rather than the other. So it looks as though either you're going to accept the necessity or you're going to end up with ultimately it's a brute contingency, which was the problem. That was the thing that was objectionable.
So Dr. Craig, quick response to that, and then we'll move through some more questions.
I have no problem with saying that God has free choices that are ultimately inexplicable. I think that that's unproblematic. The theory still has greater explanatory depth than simply postulating the necessity of the mathematical structure in the world.
But you then end up with ultimately it's a brute contingency.
Yeah. Sorry. I was trying to be short because we have a lot of questions to get through. Is that okay? If we keep moving on. Okay. Sure. And this one is from a very good friend of mine. His name is Ale. His screen name is different, but anyways, he's a very good friend. It's like a brother to me. He says, among physicists, there's actually a quote. Among physicists, when it turns out that mathematically beautiful ideas are actually relevant to the real world, we get ... there is ... some deeper truth. What do you make out of Weinberg's view? And maybe this can go to either one.
I don't understand the question. So Graham, if you understand it, go ahead.
I'm not sure that I understand it either.
What's the ... referred to?
Oh, that's an ellipsis. So he's taking some later part out of it. So let me just repeat the quote.
So can you
one more
read it
time.
without the ellipses? That might
Yes.
make it.
Among physicists, when it turns out that mathematically beautiful ideas are actually relevant to the real world, we get there is some deeper truth. What do you make out of Weinberg's view?
So what's he saying, that when you find cases where there's the applicability of surprising applicability of mathematics in the world, that we suppose that there must be some deeper explanation for why it's applicable or something like that? Is that what the quote's supposed to be saying? So, I mean, let me try a different example, a kind of example we haven't discussed so far. So Wigner mentions Borel sets as something that it's very surprising that we get applicability to the physical world. But think about Borel algebras, right? We're in the same ballpark here. Kolmogorov's theory of probability is couched in terms of Borel algebras. And we use the theory of probability to do things like explain the behavior of bookmakers, right? So is there some deep explanation for why the theory of Borel algebras has some application to explanation of the behavior of bookmakers? The quote that we were just given suggests that we should be thinking there's got to be some deeper explanation here of how it turns out that bit of rather abstruse mathematics ends up having application to the behavior of human beings. So it's got nothing. This isn't an example. It's got nothing to do with physics. This is another question that I had about Wigner's paper, that you can find these kinds of mathematical things applied to mass human behavior, for example. Mm-hmm. But anyway, I don't know what you think about that.
Any thoughts on that, Dr. Craig, or should we move on?
As Graham said, Wigner's paper is restricted to the mathematical laws that characterize physical phenomena in physics. And he's not speaking to other disciplines or areas such as biology or human behavior. That's an open question that is another day to discuss.
All right, so another super chat from David LaRosa. And I apologize, I can't get to every single super chat that was sent in. Some of them are a little off topic, so I'm skipping over those to try to cover the ones that are very pertinent to what we're discussing tonight. So this one is, should reality be interpreted solely on calculations, or is there a deeper meaning in physics and intuition plays a fundamental role in the final decision as to what route to follow?
Okay, let me say something controversial about that. So before you can accept a physical theory, what you need to have is some empirical predictions that have been successfully tested in accordance with the theory, right? We have lots of people have been working away on string theory for a long time. It's controversial amongst physicists, I believe, whether we should even count it as physics at this stage, because it hasn't been able to generate any testable predictions, right? So it can't be that and it won't be that we end up deciding that we've hit the ultimate theory because it's beautiful. If we end up hitting the ultimate theory, it will be because there's nothing that we can't predict using it or something like that, nothing relevant that we can't predict, that it's fit to experimental results is perfect. I don't know, does that answer the question?
I think so, and string theory could be a great example of mathematical equations that are not applicable to physical phenomena. And as Graham says, you need to do some testing to find out.
Okay, so we have another question from Cross-Examined in Espanol, the Spanish channel for Cross-Examined. They say, if the universe has a mathematical ontological structure, how can we postulate God as the best explanation if we do not yet have a theory that gives us epistemic access to mathematical objects?
Because the mathematical objects are not playing a role in the explanation. Mathematical objects, even if they exist, are non-causally connected or causally non-connected with the world. So the explanation is that whether you're a realist or an anti-realist, if you're a theist, you have a causal explanation for why the physical world exhibits the mathematical structure and describability that it does. And that explanation doesn't need to appeal to any kind of causal input of mathematical objects.
Graham, is there anything you'd like to add?
So I said earlier that I would kind of want to bracket the question about the ontology. It doesn't seem that that's important. It's that what really matters is something more like the objectivity of mathematics, which is not, the understanding of that objectivity is not helped by postulating objects, in my view. So.
Well,
right,
that's which we agree.
Yeah, I know. It's one of many points on which we agree.
All right, from YT, does the argument assume scientific realism?
You know, I don't think it does, because again, Wigner is very careful. He says that it allows, the mathematical equations allow us to describe with an amazing accuracy, in an uncanny number of cases, the physical phenomena. So he's talking about the way the world appears to us. And he's not taking a kind of naive, realistic view of science and the world. It could be scientific realism, but it need not be for his argument to go through.
Now, what do you think, Graham? Do you think it has to, it can only go through on scientific realism?
So this is kind of tricky, right? Sometimes people will
it'd be
present...
good. Sorry to interrupt. Perhaps it'd be good to just define what scientific realism is.
Well, that's going to be controversial too, because some people think that scientific realism is just going to be realism about the entities that are postulated by science. So a scientific realist believes in electrons and black holes and things like that. Whereas other people are going to think that you need a lot more for scientific realism than that. What you need is that your scientific theories give a true account of the world. So it's not just that they postulate the right entities, but they say the right things about them as well. And if you're kind of not inclined to think that our current scientific theories are true, that they're true in every respect, you might be a scientific realist in the first sense and think that the entities, black holes and electrons and so on, exist without going to the second step. I agree that Wigner is a bit canny about scientific realism in his paper, but some people who present the kind of discussion that we're having today are kind of less cautious. And they take the kind of important things that Wigner's talking about to be things like Dirac's prediction of the existence of positrons, or Hawking's prediction of the existence of black holes, or Higgs's prediction of the Higgs boson. Whereas in some ways, that's not what bothers Wigner most, right? I mean, and it's closer to something that Bill was talking about. So here's the sort of thing that really, I think, really bothers Wigner. And I'll give you two examples. There are different ways of formulating quantum mechanics. You can give a matrix formulation, you can give a wave formulation, you can give a Hilbert space formulation. The mathematical apparatus is completely different in each case. What's the same is the empirical predictions. So these theories are empirically equivalent, but mathematically very different. Second example, which he also mentions, is Newtonian mechanics. You can give action at a distance formulation, you can give a local field formulation, you can give a least action formulation. The mathematics is very different in each case, and as Wigner points out, and Feynman says, if you want to take one of these theories and apply it elsewhere, it makes a big difference it can make a big difference which formulation you pick. But in Newtonian mechanics, they give exactly the same empirical predictions. That makes it sound as though that Wigner's really not that interested in the question about scientific realism. What he's really interested in is just the empirical outputs. I mean, he could be an instrumentalist about scientific theories for all that we've been.
I think that's right.
Okay, 2 more questions, and then we'll close it out. So from Jonathan Thompson, he says, take the question, why is God necessarily perfect? And this one is for you, Dr. Craig. Take the question, why is God necessarily perfect? It seems that in answering that question, we can't get past the fact that that's a necessary truth. Doesn't this lend support to Oppy's point?
Well, I would say that God is by definition worthy of worship. Anything that is not worthy of worship just is not what we mean by the word God. And from that, it follows that God must be perfect. He must be morally perfect, because something that is not morally perfect, something that's morally flawed, would be not worthy of worship. So while I'm certainly willing to postulate ultimate facts, like free choices on God's part that have no deeper explanation, I think that what Graham did in his alternative theory was to just postulate necessarily that which is crying out for explanation. And that is a theory that has no explanatory depth. I mean, we can, if we're presented with data that require an explanation, rather than offer a hypothesis, we can say, well, my explanation is just, and then you just state the data. You just state it again. And that would be adequate to the data, right? Because it's just a restatement of them. But it wouldn't have any explanatory depth. And I think that's what Graham has done with his naturalistic alternative, whereas theism has greater explanatory depth, even if it ultimately arrives at a free being who freely chooses to create a world that is constructed on the mathematical blueprint that he has in mind.
Okay, so I think that's not quite true, right? Because if I just restated the data, I would have just said, here's my explanation for the uncanny efficacy of mathematics, the uncanny efficacy of mathematics, but that's not what I did. I did something else. I said, look, there's this long discussion that we've been having about the origins of the universe, and I've developed a view about how naturalists should think about this, and look, it falls out of that story that the explanation for the uncanny efficacy of mathematics is that it's necessary. And that strikes me as completely different from the way that you're describing what I did.
Okay.
All right, here's the last question. Would you be able to explain the arguments like I'm 5 years old? I'm totally lost with the big brain vocabulary.
Yeah, in my
this
debate
might
with
be a good
Alex
one.
Rosenberg, I presented the argument in a very simple, easily memorized way. Premise 1, if God does not exist, the applicability of mathematics to the physical world is just a happy coincidence. 2, the applicability of mathematics to the physical world is not just a happy coincidence, from which it follows 3, therefore God exists.
Right. So one thing I did want to ask about this is whether you were happy to replace happy coincidence with brute contingency. Because happy coincidence is kind of vague. Brute contingency is a more familiar philosophical term.
Yeah.
Yeah. And then what we disagree about is the first premise. Right? If God didn't exist, the applicability of mathematics to the physical world is just a brute contingency. Obviously, I say, if naturalism is true, the applicability of mathematics to the physical world is not just a brute contingency. Right? So
it's a brute fact, but not a brute contingency.
It's not a brute contingency, right? And so that first premise is false, and that's where we disagree.
All right, well, let's leave it there. I really appreciate both of you guys coming on and having this discussion. As I mentioned at the very beginning of this has been a long time coming, and it was a fascinating discussion. I'm sure that it was over a lot of people's heads, including my own at certain points. But either way, it was a fun discussion. I might have to go back and listen to it a few times through. But I really appreciate you two coming on, taking the time to have this discussion. It really means a lot. So I appreciate you coming on.
It's a privilege to discuss these things with Graham.
It was a pleasure. It's been a long time since we last had such a discussion, so it's been good.
Yeah.
All right. Well, if you guys would like to support Capturing Christianity and you want to help support this ministry, make sure that these things can continue happening, then the best way to do that is to go to patreon.com/capturingchristianity and pledge your support there. Monthly donations are the thing that keep this ministry up and running, so I really appreciate it if you want to help us out there. And until next time, we'll see you guys later. So have a good night.